When we talk about limits at infinity, that is just a fancy word for what you have seen as a horizontal asymptote. So certain functions, as x grows large in either direction, we use the word large negative for numbers like negative a million. Um, Certain functions become arbitrarily close to a certain number. So they flatten out and kind of glue themselves to a horizontal line. It's an invisible line. It looks like a vertical asymptote. You usually see it as a dashed line, but it happens for a very different reason. So those are called horizontal asymptotes. And now that we have limit notation, we just have a new way to kind of talk about them. So here's the graph of that function, x squared minus 1 over x squared plus 1. Um, right, you can see it flattens out into almost a horizontal line as it grows large in either direction pretty quickly. And just looking at the graph, it appears that we have a horizontal asymptote at y equals 1. So this is the new notation we use to describe that in terms of limits. We say limit as x approaches infinity of f of x equals 1. So unlike a finite limit, x is never going to get to infinity. This is just a way of saying, okay, as the function goes in the positive direction, it becomes arbitrarily close to 1. And as the function goes in the negative direction, it also becomes arbitrarily close to 1. So rather than just saying there is a horizontal asymptote at 1, we can now write it like this. In general, with rational functions, it's always going to be the same thing going in either direction. You're not going to have two different ones. So that's a big difference between these and vertical asymptotes. They don't happen because of division by 0. They just happen because, think about plugging the number 1,000 into this function. It'd be 1,000 squared minus 1 over 1,000 squared plus 1. Those numbers are very close together, right? So the function is not quite 1. It'll never quite get to 1, but it's pretty darn close. Okay, so in terms of the limit, that's really the definition here. F of x can be made arbitrarily close to 1 by taking large enough positive or negative values for x. So if you plug a million into that function, a million squared minus 1 over a million squared plus 1, whatever that number is, it's very, very, very close to 1 and can be made even closer by just taking bigger x's. So that's why it's like a limit. I just wanted to show you the only elementary function that has two different horizontal asymptotes, and that's the inverse tangent function from trig class. If you kind of think back, it looks like a trig tangent graph turned on its side, which is exactly what it is. That's what it looks like. It's got a horizontal asymptote going in the positive direction of pi over 2 and in the negative direction of negative pi over 2. So that's the way we would say that, right? Instead of literally saying there is a horizontal asymptote at pi over 2, we would say the limit as x goes to positive infinity is pi over 2, and the limit as x goes to negative infinity is negative pi over 2. So we want to be able to actually find these things algebraically. And you may have learned a trick in algebra class for doing this, and I will, in fact, show you the trick. But this algebra move is something you're going to need to do in the future. So I have to show you how to do it manually, basically. So we're going to find, when we say find the limit as x goes to infinity of this thing, 2x squared minus 100x over x squared plus 1, we just mean find the horizontal asymptote. And as I've already told you, there's only one. So it's going to do the same exact thing going to negative infinity. So here's the move. And here's the thing to remember. You're going to look in the denominator and you're going to find the highest power of x. And you're going to divide everything by it. So this is a rational function. It's a fraction. So I can divide by anything I want as long as I divide the numerator and the denominator by the same thing. And you're just going to have to trust me for now of why this trick works. So this one happens to be x squared. We're going to divide everything in the numerator and in the denominator by x squared. And that's what that looks like. It's ugly, but we can handle it. Right, so everything gets divided by x squared. It's a compound fraction. We'll live. And then we simplify it. So that first term becomes 2. The second term becomes 100 over x. The first term in the denominator is just 1. And then we have a plus 1 over x squared. So if you think back to the limit laws I had you kind of go over, they just say that we can break this thing up into 4 individual pieces and just look at all the pieces separately. whatever happens to those four individual pieces is going to happen to the same thing. So you wouldn't have to write down this next step because it's ugly, but I'm going to. So we can just individually look at the limit as x goes to infinity of 2, and the limit of 100 over x, and the limit of 1, and the limit of 1 over x squared. I didn't write the little as x goes to infinity just because you get the idea. So the first thing we're going to do is use what we call like the constant multiple rule for limits to just pull that 100 to the outside. 100 over x is the same as 100 times 1 over x. You're going to see in the next step, though, that that actually doesn't really matter, and the 100 doesn't do anything. When you see something like the limit as x goes to infinity of 2, 2 is independent of x. So that limit is just 2, right? That part of it doesn't care that x is going to infinity, so that's going to hang around. So as far as what happens to terms like the limit of 1 over x and the limit of 1 over x squared, just think about it intuitively. If x gets really big, if x is 1,000, 1 over x squared is 1 over 1,000 squared, which is a very tiny number. If x is 1,000,000, then that's 1 over 1,000,000 squared, which is an even much tinier number. So the power doesn't matter, and numbers like 100 don't matter. Anything that takes that form, 1 over x to a power, as x gets big, is going to go to 0. So we have a theorem for that, and we can just have it, and you don't have to justify it or cite it. Okay, so my little theorem says for any positive number p, the limit as x goes to infinity of 1 over x to the p is always 0. So even if p is a half, that's 1 over the square root of x, it's going to go to 0 slower than something like 1 over x to the 10th, but it's still going to get there. So now that we have that, we can just say, okay, any term that looks like that looks anything like that, we can just say, okay, that limit is 0, and it just completely drops out. Right, so our function here, or our limit here, the 100 times the limit of 1 over x is just 0. It's just 100 times 0. And the limit of 1 over x squared is also just 0. The 2 and the 1 are independent of x, so they hang around, and they're the only things that hang around. So the terms with the 1 over x to the whatever drop out, all you're left with is 2 over 1, which is just 2. So that's the horizontal asymptote. And if you wanted to check that, you would just have to graph it and either like punch in a big number on a table or just literally look at the graph, and you should see it just glue itself to y equals 2. So you'll notice a pattern here that I'll summarize at the end. The 2 and the 1 were the leading coefficients, the coefficients on the highest powers. They're the only things that hung around. That 100 could have been 1,000 or 1,000,000 or pi or whatever. It didn't make any difference in the final result, and that generally is what happens. Okay, let's do another one. Same exact algebra, so I'll probably go through it a little faster. 1,000 x squared minus x over x cubed plus 3x squared, and you'll see a similar thing happening. The terms like 3x squared and stuff don't end up doing anything. So we're going to divide by x cubed being the highest power of x we see in the denominator specifically. It's the one in the denominator, so write that down. That's what it looks like. It's ugly, but you can see everything's about to simplify, so simplify it. We get 1,000 over x minus 1 over x squared over 1 plus 3 over x. And now the same thing's about to happen. Everything that looks like 1,000 over x or 3 over x or 1 over x squared, all that stuff goes to 0 as x becomes large. So you can just say that. You don't even need to, you just put 0 in there. So we're breaking it up into those 4 separate limits, but we're going to skip that step because we don't really need to write down what we're doing. Okay, so every one of those something over x to the something goes to 0. So it's just 0 over 0, or I'm sorry, 0 minus 0 over 1 plus 0, which is 0 over 1. Not to be confused with 1 over 0. 1 over 0 is undefined. 0 over 1 is fine. 0 over anything is 0. So that limit is just 0. So if you looked on the graph, there would be a horizontal asymptote that was just the x-axis, right? It just goes to 0. Okay, so here's where I summarize it and make it easier. For a rational function, now the function like that you're looking at right now isn't exactly a rational function because it has a square root in it, but I'm calling it a rational type function, which is a word I made up because it just looks like one and it obeys all the stuff I'm about to say. So if there's a square root or any kind of fractional exponent, this stuff all still applies. So anything that looks like this. If you have a horizontal asymptote, it's going to be the same one going to infinity as it is going to negative infinity. That's just how it happens. And there are only three things that can possibly happen. So this first case is the first problem we saw. If the highest powers of x, right, we would call that the degree of the numerator and the degree of the denominator, except that that numerator isn't really a polynomial, but who cares? So the highest power of x, if they're equal, then all that matters is the leading coefficients, which are 2 and 4. So the coefficients on the highest power of x, those little numbers before it. And you can kind of just imagine doing this in your head. You divide everything by x to the 4th. Everything except the 2 and the 8 would look like one of those, like, you know, it'd be like 99 over x. It would look like one of those something over x to the something things. So all those terms would go to 0. The 2 and the 8 would be the only thing that hung around. So the horizontal asymptote would just be a 2 over 8, which is 1/4. If this were the kind of math class where I had you show your work, then you could just say that. Degree of numerator and denominator are equal. So that's just 2 over 8. It's just those coefficients. So you could jump right to there. Case 2 is like the example we most recently saw. If the highest power appears in the denominator, then it just goes to 0. So again, imagine doing that algebra move and dividing everything here by x to the 5th. Everything except the x to the 5th would go to 0, and the x to the 5th would just, in this case, go to 1. But it would all still just be 0 over 1, which is 0. So just think about that no matter what's up top, the denominator wins this race. Because 1,000 to the 5th is way bigger than 1,000 to the 4th, and when you get into even bigger numbers, the denominator is going to win, which just means the whole thing just goes to 0. So you can just say that. Denominator has higher degree. Horizontal asymptote is 0. And then the third case is, the only other case is if the numerator has the bigger power. And if that's the case, the opposite happens. The numerator wins and the function either gets really, really, really big or it gets really, really big negative, and this stuff just doesn't apply. So you could either say the limit does not exist or just that there is no horizontal asymptote. So other types of functions have limits at infinity and horizontal asymptotes, exponential functions, trig functions and stuff. So these rules don't apply there. There you would have to, I don't know, do some math. But for what we need to do right now, you can always do that algebra move where you divide, or you can just cite this 3-case thing. There's only 3 things that can possibly happen. Either it's a number, non-zero number, or it's 0, or in the third case, there just isn't one because the numerator just blows up out of control.